To our friends, team members, and customers in the US, thank you for spending your early morning hours with us. Right now, it's 9:03 New Zealand Daylight Time, and we're 14 minutes away from liftoff at LC-1 on the Mahia Peninsula. We've got a 2-hour window today. You can keep up to date on our launch operations by following Rocket Lab on Twitter and Facebook, as well as checking in on our website. Keep up to
And at this point, confirm your monitoring mission code and ALE code.
Can confirm. RCO flight mission.
Go ahead.
Please open the LC-1 launch switch cover and confirm.
Switch covers up.
Please toggle abort switch. Confirm.
Toggle confirmed.
Okay, please keep the LC-1 launch switch cover open from this time.
Switch covers up.
RCO, please confirm you're actively monitoring mission cord, range cord, and safety net.
Confirmed.
Today's flight is a commercial rideshare comprised of a diverse range of small sats destined for low Earth orbit. Unfortunately, there won't be live footage of payload deployment, but here are the details of the 7 spacecraft we're flying today. 6 of the 7 are comprised of 5-centimeter pocket cube pico satellites from satellite manufacturer and mission management provider Alba Orbital, which together represent 5 different countries heading to space. These picosats include a 2P payload from Advanced Technology of Laser, which is located in Hungary, that's designed to test a new thermal isolation material in space. There's a 1P pico satellite developed by Spanish nonprofit organization FOSSA Systems that uses low power radio frequency to provide IoT connectivity. We've got a pair of 3P pico satellites from Stara Space, which aim to demonstrate LEO-to-LEO inter-satellite link technology. These spacecraft are utilizing Alba Orbital's Unicorn 2 platform. Another Hungarian satellite, SMOG-P, a 1P picosat, this time built by students at the Budapest University of Technology and Economics, and it features a spectrum analyzer to measure human-caused electromagnetic pollution from space. The 6 pico satellite comes from a US-German software development company, Acme Atronomatic, and it has a satellite on board which will help the company provide flight tracking services to the aviation community and to mobile applications for things like MyRadar, which is a radar-based weather application for mobile devices. The 1P picosat also bears the logo from the computer game Star Citizen, a popular crowd-funded space simulation. The 7th and final payload on board aims to simulate the visual effects of meteors entering the Earth's atmosphere for a Tokyo-based company called ALE. The mission was procured by Spaceflight, a satellite rideshare and mission management provider. Today we'll be deploying our first payload to a circular 400 by 400 kilometer orbit at around 97 degrees inclination. After this deployment, the kick stage's Curie engine will reignite to reposition the stage in a 385 kilometer orbit to deploy our second payload.
And please disable recovery battery charging.
Confirmed.
GC flight mission.
Flight GC.
Please send pre-valve open command and confirm.
Pre-valve is commanded open.
Like me, I'm sure a lot of you are excited about what this mission represents for Rocket Lab's Stage 1 reusability plans. Back in August, we announced our plans to develop a system to recover Electron's first stage for reuse, and this flight marks a significant step forward in those plans. We've completed a block upgrade of the first stage, incorporating guidance and navigation hardware, including S-band telemetry and onboard flight computer systems. These new flight systems will gather data during the first stage's atmospheric reentry after separation from Electron's second stage. The first stage is also equipped with a reaction control system to orient the booster during its reentry descent. On your screen, you might be able to make out some of the new sensors and hardware we've installed in the booster to shape these recovery efforts. Today's first stage is a sacrificial booster, and we won't be recovering it, but the data we gather from this operation will help to inform our future recovery efforts. Now, we may be able to show footage from Stage 1's cameras as the booster re-enters the Earth's atmosphere, but this will be limited by the quality of the video signal at that point in the mission. During re-entry, you may see what looks like flames or a red-orange glow around the booster. This is completely normal and is expected. As the stage re-enters the atmosphere at 8.5 times the speed of sound, it creates friction with the surrounding air. This friction causes the air molecules to generate a very hot plasma, which can glow red or orange.
Avionics flight mission.
Flight avionics.
Please cycle vehicle camera recordings and confirm.
Camera recordings have been restarted.
GC flight mission.
Flight GC.
Please enable ground high-speed logging and vibration logging.
High-speed logging and vibration logging are enabled.
And please confirm that igniter pressures are in bounds.
Igniter pressures are within bounds.
Stage 1 flight mission.
What's stage 1?
Please confirm stage 1 tank press set point locks 400 kPa Kero 225.
Confirm both.
Stage 2 flight mission.
Flight stage 2.
Please confirm igniter pressures are in bounds.
Confirmed.
And please confirm Curie catalyst preheat is disabled.
Confirmed.
Stage 2, please confirm the stage 2 tank set points to 365 locks and 205 Kero.
Affirmative.
Avionics flight mission.
Flight avionics.
Please confirm stage 2 HVBs are enabled and hot swap is ready.
Stage 2 HVBs are enabled and hot swap is ready.
And avionics, please confirm all stage 1 HV batteries are enabled.
Stage 1 HVB bats are enabled.
Stage 2 flight on mission.
Flight stage 2.
Please confirm stage 2 engine is ready.
Confirmed.
And stage 1, please confirm all stage 1 engines are ready.
Confirmed.
And GC RCO mission cord.
RCO GC.
Disable all HVAC and confirm.
Stand by.
Beyond our recovery plans, we've added another exciting change to our manufacturing processes to make weekly Electron launches a reality. Her name is Rosie, and she's a custom-built 140 square meter robot that enables the precision machining of Electron's carbon composite structures. This includes stage 1, stage 2, and the fairing. In just 12 hours, all marking, cutting, drilling, milling, and sanding is completed on a full vehicle. It's a job that used to take around 400 hours by hand. Here's our founder and CEO, Peter Beck, to tell you more about Rosie.
We've just stepped inside Rosie the robot, Rocket Lab's newest piece of automation equipment. This machine, as you can see, is absolutely massive. You can literally park a school bus on this, it's that big. But what this machine does is it takes every single carbon composite component of the launch vehicle and processes it ready to move on to the next stage of production. Now what Rosie really means for Rocket Lab and our launch frequency is we're able to process launch vehicles so much faster. Traditionally, you talk about rocket manufacturing in years. Then you start talking about it in months, weeks. Well, we talk about it in days. Raw materials come in, rocket comes out in a matter of hours. It's every bit of marking, every bit of machining, every bit of drilling, all the operations you can imagine. It literally takes hundreds of hours, and we can produce one launch vehicle in this machine every 12 hours. What you see here is a second stage of Electron, getting the final post-processing completed on it, ready to ship out to the production line.
Rosie is automating machine tasks, but human hands are still in high demand in Rocket Lab's manufacturing teams. We'll be recruiting over 100 manufacturing test and design engineers into the company over the next 12 months to keep up with our production demands. There are roles in our New Zealand and US locations, including at our second pad, Launch Complex 2 on Wallops Island in Virginia. Work began on LC2 in February, and in just 9 short months, more than 1,400 cubic yards of concrete have been poured at the site. Recently, the 65-ton launch platform was installed into its final position, and the 44-foot strong back has been mounted and secured, ready to support Electron on launch days. Work has now moved on to testing, commissioning, and integration of the site infrastructure and preparation for the first Electron launch from U.S. soil, slated for early 2020. LC-2 will bring a new launch capability to the nation and is tailored specifically for government missions across science, research, and national security. A huge thanks to the teams at Virginia Space, Mars, and NASA Wallops. The drive and dedication you and our many local suppliers have shown has been key in helping us build this pad so quickly. We can't wait to officially open the pad in December with our first flight scheduled in the coming months. As you can see, we only have 4 minutes left in the countdown, so I'm going to hand you over to Mission Control and I'll be back with you just after liftoff.
Copy that. Strong back is retracted for flight. Hold on mechanisms armed. Range is green, auto seam is enabled.
Avionics, flight on mission.
Light avionics.
Please disable stage 1 transmitter fan.
Stage 1 transmitter fan is disabled.
And please confirm stage 2 MB POF is nominal.
Stage 2 umbilical POF is nominal.
Recovery, please 0. Stage 1 recovery nav. Positioning confirm.
Confirm, ANU position 0'd.
Okay, all stations from now on, there should be no red flags on your LCCs. The vehicle is green and ready for flight. VMS flight mission.
Go ahead.
Confirm as goes the green.
As goes the green.
Please lock auto sequence and confirm.
Auto sequence is locked. Flight computer is ready.
Okay, and all stations, we now go for auto sequence start in 5 seconds.
And recovery system is green as well.
Avionics flight mission.
Light avionics.
Please confirm all AV bats have been switched to internal power.
All AV bats are on internal power.
Confirm stage power is disabled on all 3 stages.
External power to all 3 stages is disabled.
All stations, be advised, vehicles now on internal power. PLS flight mission.
PLS locks.
Please begin lock skid recirc.
Recirculating.
PLS flight on mission.
PLS copy.
Please disable anti-geysering and confirm.
Pressing Kiro.
All anti-geysering disabled.
Stage 1 flight mission.
Flight stage 1.
Please confirm stage 1 tank suppressed.
Confirmed.
Stage 2, same to you.
Yeah, confirmed.
Engine purge active.
AV battery checks. Commanding deluge start.
Deluge running.
Readying GNC systems. Pre-readying engines.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning pitch over.
Stage 1 propulsion is nominal.
Enter chevron 1.
There it goes. Rocket Lab's 10th Electron has now left the pad and is on its way to space. With over 1 million horsepower at its back, running out of fingers will quickly reach the toughest point in its battle against
battery
physics,
discharge nominal.
the moment known as maximum aerodynamic pressure, or Max 2. So let's check in on Electron's performance.
Enter chevron 2.
Vehicle is supersonic. Approaching max Q. Cleared max Q. Guidance is nominal.
We've made it past Max Q, and Electron continues nominally. Soon the 9 Rutherford engines on Electron's first stage will shut down ahead of its separation
AOS
from
Chatham
stage
Station.
2 and its descent back to Earth. It will be our first attempt at a
Stage 1
guided
propulsion
atmospheric
holds
reentry of the
nominal,
booster,
prepare for
and we're hoping to be able to
approximately
update you
30
on how that goes after the mission. Once stage 1 and stage 2 have separated, the final vacuum-optimized Rutherford engine on Electron's second stage will come to life and propel Electron the rest of the way to orbit. Let's check back in on the operators in the lead up to stage separation and stage 2 ignition.
Staging in 15 seconds.
Doing burnout detect mode.
Stage 1 MECO.
Stage separation succeeded.
Stage 2 ignition.
Recovery telemetry nominal.
Main engine cutoff is now confirmed, and Electron's first and second stages have successfully separated.
Guidance is nominal.
Soon the fairing will
Speed
separate
is
and jettison from
2.3
Electron's kick
kilometers per
stage, so let's
second.
watch.
Altitude 104 kilometers.
Fairing separation succeeded.
Stage 2 propulsion is nominal.
Looks like we've had a successful jettison of the
battery
fairing.
discharges.
With that out of the way, we're now 50 minutes away from the start of our scheduled payload deployment. As you can see on your screens, Electron's second stage Rutherford engine continues to burn bright as it propels its payloads into orbit. And on the left, we have visual of stage 1 during its first controlled re-entry into the Earth's atmosphere. The data we receive from this guided re-entry will aid in our future recovery plans. We'll continue to broadcast this view as long as we can
Stage 2
for you.
propulsion is nominal.
HVB battery discharge is nominal.
The next milestone to check off is one that's unique to Rocket Lab and Electron. The Rutherford engines are powered by electric pumps. Electron is in fact the world's only orbital launch vehicle with this feature. These pumps are powered by batteries, and as you can imagine, it takes quite a bit of power to reach orbit. Initially, a pair of batteries serves as the power source, but once these are depleted, we swap power over to another fully charged battery and then jettison the depleted ones. We call this process the battery hot swap.
Guidance is nominal. 185 seconds remaining.
Electron's velocity is 14,000 kilometers per hour, and our altitude is 200 kilometers as we approach battery hot swap.
HVB battery discharge nominal, approaching hot swap in roughly 30 seconds. The AVS has saved. Hot swap successful.
HV battery eject succeeded.
As you've just heard, we've had successful battery hot swap. Electron's second stage engine
Recovery system
continues to burn
reorientation
6
successful,
minutes and 45
enabling
seconds
access
into the
imminent.
mission. We're currently 7 minutes, 15 seconds into flight, and with the mass of the depleted batteries out of the picture, Electron now has a much more efficient ride to orbit. All systems are nominal as we approach second engine cutoff in around 40 seconds. Our velocity is 21,000 kilometers per hour, and our altitude
HVB
is
battery discharge
204
holding
kilometers.
nominal.
Shortly we'll have cutoff of the vacuum-optimized Rutherford engine on Electron's second stage, followed by separation
Guidance
of the kick
is
stage.
terminal.
Let's check back in with mission control.
Entering stage 2 burnout detect mode.
Stage 2 shutdown.
Vehicle is in transfer orbit. Apogee is 385.97 kilometers. Perigee is 186.01 kilometers. Inclination 97.01 degrees.
And we have confirmation of kick stage separation. Electron's running out of fingers mission is now orbital. As I mentioned at the beginning of the webcast, we won't have live footage of payload deployment scheduled approximately 45 minutes from now, but you can follow us on Twitter and Facebook for confirmation that all satellites have been deployed. Before we leave you, a final thank you to our mission partners for choosing to fly with us on our 10th Electron mission and final launch of 2019, and a massive congratulations to the Rocket Lab team on 10 flights. It's been a huge year for us with 6 orbital missions. We've got planes to look forward to in 2020 with our first launch from ALE-2 in Virginia, the first launch of Photon, our customizable satellite bus, and of course our future recovery attempts of Electron. All this means there are still plenty of exciting career opportunities here at Rocket Lab. If you've ever thought about joining our world-class team, head to rocketlabusa.com. Thanks for the ride in 2019, and we'll see you back here in 2020. I'm Max Muncy. This is Rocket Lab Mission Control, signing off.
Hi, it's me, Tim Dodd, the Everyday Astronaut. We're at a really exciting time where the number of crewed vehicles going to the International Space Station will go from just 1 to 3. The Soyuz's 8-year monopoly for getting humans up to the International Space Station is finally coming to an end. So today, we're going to take a deep dive on the 2 new spaceships that are going to be responsible for taking humans to and from the International Space Station from the United States. So we're going to compare the Boeing Starliner riding an Atlas V rocket to SpaceX